This tutorial is about QTCAD, which is a product of Nano Academic Technologies. You can go to their website to take a look. In the last few video, there was a video I taught about how to use Gmesh to create a structure. In this video, we will use something called Builder. Official name is QTCAD Builder to create a structure. It creates a structure based on GDS, which can make it more flexible and easier to make a complicated structure, right? So we will look at an example based on the tutorial. We go directly to semiconductor, a practical application. And we will start with this germanium-based gated double quantum dots. So let's see what we are trying to do here. Our goal here is to load a file, a GDS file in OASIS format. It's ge_dqd.oas. And this is the GDS. And this is the stack from substrate to silicon germanium barrier, germanium, CAD, and then oxide. If you know, you should know that silicon has a band gap of 1.12. Germanium is about 0.67. There's an offset, particularly at the valence band. So if we have an alloy with more silicon, you expect to have a wider band gap. So there will be an offset so that you will confine the hole inside germanium. So to explain this, let me sketch this a little bit. Right. So when it is germanium, you likely have a small band gap. For silicon germanium, I forgot how much the offset is for the conduction band, but for valence band is pretty large. So you will have something like this, right? So this is CAD, silicon germanium CAD, 5 nanometer, and this is the silicon germanium barrier, 40 nanometer, right? So as a result, you will be able to confine the holes here and form a well. Now this is in the vertical direction, right? This is the Z direction. Now then with the confinement from the top view, right, you will then be able to form a quantum dot, okay? But we won't go into detail, just an idea, right? More importantly, in this tutorial, we want to talk about the how to create the structure using QTCAD Builder. Now, first of all, you see that it's a Python code, right? So it is different from Gmesh, which has different input syntax. This is a Python code, so you see that everything is in Python. I'm going to copy this, right-click, place. Now, again, because of I'm not running from scripts, right? I am doing everything using Python, so I'm going to just make all the relative directory to the current directory. And because this is a string, so I will just use plus. I do the same thing for the rest. Okay, and I have an output file. I'm going to remove this because this command only works for the file, for the path object. I forgot what's the name, right? It doesn't work for string. Okay, so this is the initial setup. Import the builder. The builder is a part of QTCAD, and again, you can look at details from the tutorial. Now then, we will set some variables. Nothing special. This is just a characteristic length for it to set up the mesh. At the quantum dot region, it has a smaller length, so we have a denser mesh. Here, say that, okay, the gate has 10 nanometer. If you go back to here, 10 nanometer of aluminum oxide, 5 nanometer of CAD, 20 nanometer of well, right, 40 nanometer of barrier, etc. right? So these are just variable. We are setting up the variable. Enter, enter, right? Now, then we need to load the layout. Now, the point is that where is the layout? So the layout, as it mentioned here, you can copy from the installation, example, practical application, whatever, Oasis, right? So I already did that. Right? You can take a look at my local directory, ls. So actually, I copy it to this folder. So now I actually forgot about this, but that is okay. So I will just copy the file OAS to here. Let me see what I did wrong. Okay, I see what's inside. Copy silicon germanium. I should have the actually cannot find it. So one possibility is that I accidentally removed it earlier. So let me copy it again. So dot, right? I go back one more level and then I try to see what I have. Example, right? Tutorial, and then should be silicon. I forgot, so I better just come to here. Germanium hole. No, actually it should be practical application. Germanium hole, right? And then layout, and then here. Okay, so maybe it's under layout actually. So I copy already, but yeah, so it is actually I copy under layout. But anyway, I'm working in a new directory under this test. Okay, so a little bit messy, but I do have the file here, right? GE double quantum dot OAS. So the first thing I will just load it. Okay. Now again, I need to be careful. I already defined the layout directory, so should be okay. I will just enter. But actually I have a problem, right? If I use up arrow key, I see that I actually have a problem because I'm using this this command, which only work for the path object, right? Not string. This might work or might not. Let me see. So it has some problem because I actually did not put it under layout. Okay, so let me just remove this. Right, you see that you try to, and I forgot the slash, but you try to have this layout append to it, right? So I'm just say that this is local path. Okay, now it's loaded, right? When it's loaded, you try to print the tree. It tell me that there are 4 different layers, 1, 4, and 0, and each of them has some region, right? So if you have a tool to look at the layout, that would be the best. For example, now let's look at K layout, which I opened already, right? Remember I say you have mask 1, 4, and 0. Let's take a look. This is 0. Let me double click to turn them off. This is 0. It is the substrate, right? So substrate 0, right? You only have 1 polygon. Okay, and then how about 1? This is the dotted region. This is the region where we call it a quantum dot region. We are going to solve both the Poisson and Schrodinger equation. So again, this only has 1 polygon. And how about for gate? It is 4, right? Look at this. We have gate 1, 2, 3, 4. Okay, so so then we have everything here. But more importantly, these polygons are also associated with some name. Okay, they're already put on the layout, and that's why you can extract it. So if you create your own layouts, you want to assign the polygon with the name also. Okay. Now one more important thing is it talk about that if we look at the command, right? The command said the cell name is top. If we look at K layout, you see that it is top also. Okay, so I think that's it. That's what I want to say. Okay, now with this, then we move forward. You print this everything. So now the point is, how do we build the structure? Okay, so we do this step by step. The first thing is that let's just copy this command, right click and paste. Right, it's trying to build something, but what does it do actually? It say, okay, first you try to set the mesh size as the characteristic length. Remember earlier we set the characteristic length to how much? I also forgot, to 5 nanometer, right? So it's going to make the mesh size to be about 5 nanometer. And it used the mask substrate. Now, what is mask substrate? Let's take a look at here again. It means use this mask 0. So it is the big one, okay, which is this one. If I look at the K layout, right, which is this one, this box, okay. And again, in K layout, you can type Q, and then you will see the property of this box, right? Look at user property, you will see the name is substrate, right? And similarly, if I click on this one, Q, look at the property, you see this is BR, which is one of the barrier gates. So it's used this mask, and what is it going to do? It set it as the name as substrate, and then it's going to extrude it for that thickness. Okay, so it is going to do extrusion for each layer, right? So imagine you only have the mask, but you keep extruding based on the thickness of each layer. Okay, but what will we get? It will be easier to see if we look at the final result, right? So now we go here. It has the builder view. I copy this, right click and paste, enter. Okay, so there's a problem because we also try to save the file, but here we don't have the output directory. I mean, we have the output directory, but I would like to just put it into the local directory. So I just use string. Okay, do you see that? First of all, it use Gmesh for viewing. Okay, this is just for viewing. It's not constructed by Gmesh, just to view it. You see that it used this big square, which is this rectangle, not square, right? This rectangle, this one, right? To build this base and then extrude as a region called substrate by that much of thickness. And then silicon barrier is difficult to see the name, right? Germanium well, silicon germanium cap, and then oxide. Okay, and I can close it now. But more importantly, it also saves something called heterostructure, right? So this is a file we can open it if we really want, right? We can come here and then open it. I actually don't know how to open. I just press the alternate key and then open. And I don't think I'm at the right location. I will go to QTCAD new here, and this is the file I just saved, right? So this is just a picture, okay? So you save it there. Okay, so if you're not familiar with builder like me, actually I'm not familiar with this, right? You can always go to this builder, TCAD builder API and take a look on the package. And then, for example, right, extrude, right? Then it will tell you how extrude works. Okay. Okay, great. So that is to build the stack. Okay. Now the next step we will do is to define the quantum dot region. Now this one, it can be a little bit confusing, but let's do it step by step. First, I copy it, right, and right click and I paste. Okay, so what does it do? First, it just define a variable called dot height. How high is that? Is the thickness of the germanium well, which we defined earlier, divided by half of the cap, and then plus silicon 20% of the silicon germanium barrier. So what you try to do basically is say, okay, I'm going to define a region with the thickness which is about 1/5 into the silicon germanium barrier, and then half into the silicon cap, and then of course include the whole germanium well. So it will be this region where we call it quantum dot, and we are going to solve both the Poisson and Schrodinger equation, right? And then we also need to find the starting point, right? We only talk here is only the thickness, right? And starting point, we use the builder option. It has a function that gets Z from group. So it's like you go to the germanium well, right? So you get this one germanium well, then you will get this point, the coordinate of this point, the Z, right? Because we say bottom yellow true. And then we subtract this by 1/5 of the germanium barrier, right? So we got the bottom and subtract by 1/5 the germanium barrier, then we know what is this point, right? And then we add back the thickness that we want, then we will include the whole region, okay? And that is what we are doing in the next command. We copy, right click, and paste. Now, again, I have this problem just directory. It's okay, no worry. Let me just delete it and run it again. Right, now it pop up Gmesh, and do you see that? I can click on it and rotate. Now, first of all, it uses a smaller rectangle, right, than the substrate one. And I pan it by clicking on the right button. And if we look at the K layout or the layouts, right, you see this one, you type Q, user property, this is the dot region, right? Dot region is smaller than the substrate, which makes sense. That's exactly what we're seeing here, right? So you see that this is the dot region, which is smaller. And then how high it is, based on this, you see that it does, right, go into 1/5 of the barrier, half into the cap, right, and contain the whole region. Now, however, we already defined the region before. Now this is an intercept, right? It is a union between two regions. But that doesn't matter, right? So let me just rotate it. It's difficult to rotate. In this way, right? You see that for those new region, it actually becomes silicon germanium barrier underscore dot region, germanium well underscore dot region, and then germanium cap underscore dot region. And that is what it is said here in the tutorial. Basically, we have an overlay mode, right? So here, let's explain what it is doing, of course. We build, again, now we set the starting, set Z, where we start building. We use the starting point where we calculated earlier, which is 1/5 into the germanium barrier, right? And we allow overlay, and then we talk about the size, right? Instead of characteristic length, this time is dot characteristic length, which is half of the characteristic length, which we mentioned earlier, right? And we use this mask, right? And then we group from the shape and then do the extrusion for this amount of height, right? And we build it already. Again, we have this model.dar. If you want, you can press alternate file and then open file and then model.dr. Right? And of course, we need to expand this, otherwise difficult. This is just a picture, right? This picture tells us how it looked like, and it's zoomed in by one. And that is exactly what it is mentioned here. So you see, this is very fast compared to using Gmesh, right? Now, I need to build a gate. The gates are what? If we take a look here, these are the 5 gates. And the goal is that we are going to create apply the potential, for example, with positive voltage, so that you lower the, maybe negative because it's hole, right? So you attract the hole, increase the electron potential. So you will capture a hole here and capture another hole here. And this is the barrier, right? That will create the barrier for the hole, right? So let me explain a little bit, right? You have, goal is to have this. Okay, and this is the valence band. So this is the barrier here, right? Q. This is what do we call it? User property BR, right? And this is, I believe this is P1. Oh look, puncher gate 1 will be here, right? And then this is BC, the center barrier. this must be P2, and this must be BL, the left, they call it left, no, this is plunger gate, I'm sorry. This is BL, right? The left. Although you say left and right are swapped here, but doesn't matter. Just because if we rotate it by 100 degrees, left will become right, right will become left. And this is where you put the hole. Remember, this is hole, right? So I expect this to be a positive voltage. This to be a negative voltage. This two will be negative voltage. Okay. So with that, then let's come back to here. Now, we are going to assign the gate. We copy. Let's copy first. And I'm going to paste it. So what are we doing here? Right? Again, I have this string problem because we want to save the file. So I'm going to just erase this one. Enter. Okay. Now, it then showed this 5 gates, right? And this is just why is only these 5 gates? Where are other things, right? I can rotate it. I hold the left button and rotate it. Where are the other object? They are still there. It's just that when I display, I say I only want to see this. Now, we can play with this a little bit. For example, how about instead I should not build again. I likely will just maybe just use view, right? For this 2, I want to save another file. Instead of BL, I add substrate. How about substrate? Right? Let's see what will happen. Do you see that? Now I don't have BL, but the substrate is here, right? So basically what it does is just for us to view and turn on and turn off the region. Okay, so here we have created another 2 file, right? Alternate file, open. One is the surface, right, that we seen earlier to create all these things. And then another is the one that we I just modified to illustrate how it works. Right, this is with the substrate, but again, it's top view. That's why you don't see anything, see it well, right? Okay, now, so great, we created the boundary already. Now the next thing is we need to generate the mesh. So I'm going to copy and paste, and I will not use this slash. I will just use plus. So what it does is that it uses an algorithm, special meshing algorithm, and then to write into a file called .msh. Okay, so let's it run. So it's running. It tells us how many nodes it has, and it wrote it to the file, so to the folder, right? So we take a look, right? We do have this mesh silicon germanium double quantum .msh, so it was successful. Now there is also another thing we can do is this XOA file. The goal, again, I need to do plus because I'm not using the right the object, right? I'm using string. So another is this file. This actually is the so-called boundary file. I will call it boundary file. Mesh contains all the details about the point throughout the space, and this is basically just the boundary. So if you try to take a look at the, for example, the file size, right? So actually, I was not successful in writing the last one. Okay, because of the name. I probably shouldn't, because mesh guide plus dir is actually a string called mesh. So I was wrong. It was not successful. So I write it again. And now you see that it becomes, now I do get GEDQD, right? And here I have an XAO. I have XAO, but again, this is not the thing I want. I should not have the mesh directory. So I would just enter, right? So now I do have, you look at this, I do have, where's XAO? Here, this is GE, DQTXAO, it only has 41 bytes of kbyte of memory, right? But if you look at GDD mesh, it is 400. So this is 100 times larger than this, which is understandable, right? Because one only describes the boundary and the other has all the mesh information. Okay. Okay, now then we will just take a look what it looked like. We already built it. So here, what it does is that it will output the mesh. This again for view, right? And again, I will just put mesh.peg. The first one, we show the whole volume. And the second one, we only show the quantum dot region. Okay. And it will display using Gmesh through this builder view, and then you will save the file as mesh.png and then as mesh_dr.png, and you have a certain view angle, right, in your 3D space. So let's take a look, right? So now this is the mesh. It's really big, right? And we can rotate it. Do you see this 5 contact? Right, and you definitely can compare this to what you see in K layout, this 5 contact, right? Going to close it. After I close it, it pop up the other window. This is the quantum dot region, right? It's embedded half of the cap through well and then 1/5 of the barrier. The mesh is even denser than what we saw for the through structure. Okay. Good. So we created the structure already pretty successfully. Okay, now with this, then we are done with how to use QTCAD Builder to create a structure and build a mesh. And then the next step is to use it to run simulation. And we will do it in the next lecture.